All right, so the idea of electric charge in section 17.1, we're going to take a look at three objectives. First, we're going to take a quick look and understand the basic properties of electric charge. Okay, we're going to look at the basic properties of electric charge. Second, we're going to look at the difference between conductors and insulators. And then third, we're going to distinguish among charging by contact, induction, and polarization. Three methods of which you can charge different materials and particles. To begin, let's quickly define what an electric charge really is. An electric charge is when a material has either an abundance, meaning more electrons, and thus it's negatively charged, or it's missing electrons, and thus it is positively charged. Or, in general, something could also be what's called a neutral state. The idea here that you really want to gather is that it's a transfer of electrons that causes charge. A transfer of electrons, not a transfer of protons. If, I don't know, Nina, if you're, like, sometimes you're sweating, right? That kind of material will get static electricity on it. You're not ever gaining a positive charge. You're either losing electrons to thus gain a positive charge, or you're gaining electrons to gain a negative charge. So if I'm, say, this surface here, oops. Here's surface 1. Let's say it's like somebody's sleeve on their shirt, right? Here's surface 1, and here's surface 2. Let's say surface 2 is usually, and I'm going to go through a demo of this tomorrow, but if you take like a glass rod and a piece of like cloth or felt, you can charge that by actually just rubbing it on the surface, and we're going to see a video of it. But let's say there's another particle over here. Okay? Now, if this particle is rubbed up against something like hair or wool, it'll gain a net charge. And you've seen that before with like your carpet. If you've ever rubbed your feet on your carpet and then touched somebody, you go, ooh, did you feel that? That was static electricity. I didn't even mean to do that there, but that actually worked. But usually with a carpet, because of the material it is, you gain charge. Now, you're not, again, ever changing positive charge. So if this sleeve ended up being all negatively charged, which causes this particle to be positively charged, here's what happened. What happened is electrons flowed in this direction. That's all that happened. There's no change in positive charge. It's the electrons that are moving from one surface to another, causing an imbalance in each of those two materials. James?
So, if it's electrons traveling from one thing to the other, then in a situation where there's a shock between two people, why do both of them feel it if it's a discharge from one to the other?
It's the flow that you're feeling. Okay. It's the flow. When your body feels an electric charge, even when you get like electrocuted if you touch a live wire, it's flowing through your body. So when somebody touches you, it's leaving your body, flowing into theirs, but it's still flowing through both of yours into the ground. What's happening is this, ready? If my body has a net charge on it, and my shoes are made out of rubber, the bottom of them, my shoes are insulators. I'll get into insulators in a minute and conductors. But my shoes are insulators, they're made of rubber, they're not going to transmit electricity. So if I were to charge up somehow with electrical charge, it's not going to transfer to the ground even though it wants to. But if another person I touch and they're a conductor, it'll transfer by contact into that person. Okay, it flows through them. It's not like it's trying to think of another way to put it, James. It's not like it's flowing through their body into the ground, but it's just flowing from your body to the other person's. So when there's motion of electrical charge from one person to the other, you're both going to feel it. Because I'm going to feel loss of electrons, and the person will feel gain of electrons. Does that make sense?
Yeah.
You're trying to come to like it's an equilibrium really of charge. And that's why when we talk about electric charge, we say that it's conserved. There's an equilibrium that you're looking for. So if there's a certain amount of charge in a body, and I were to touch another person's like hand with mine, then they become an equilibrium. The two people are at a state of equilibrium, so there has to be a change of charge. Just like momentum and energy conservation. Some examples of things that could be charged, like spray paint, for any artists out there. Those little aerosols, those particles, are electrically charged. That's what causes them to stick to the surface. Okay? Same thing with hairspray. Ladies, a lot of ladies use hairspray. Those are positively or negatively charged. Anybody know, and this is going, sorry gentlemen, you might know this, but ladies usually know this, Ever get like when your skirt sticks to your legs? It sticks to like your what are those? Tights, right? What do you do? What do you do to get rid of that static electric charge? Anybody know the trick?
Touch the wall.
Yeah, you spray hairspray. Because hairspray is electrically charged, it neutralizes it. What's happening is your skirt that's rubbing against your tights or whatever, there's another word for it, they're not called tights. Stockings. Stockings. So when your skirt rubs against your stockings, it creates a static electricity charge, an overall imbalance. When you spray hairspray, it neutralizes it. Same thing happens with guys. Sometimes your pants will stick to like the hair on your legs, right? You ever notice that?
Yeah.
If you have like a pair of like wool pants in the wintertime, wool pants in the winter will sometimes stick to the hair on your legs as guys, and you get that like look, like almost like the pants are like sucked to your leg, like a vacuum. It looks kind of weird, but that's what's happening here. If you sprayed hairspray, it would actually get rid of it. Although I don't know if hairspray ruins materials, if you should really be spraying it on there. So, changes.
That's actually how they paint car body panels, is they get the body panels to be
Absolutely right.
positively charged and the paint to be negatively charged, and then they spray that onto it and bond permanently.
That's exactly right. When the car is going through a production line, they purposely positively charge the actual car, and the ions are negatively charged. So the paint that's actually sprayed on there, every speck of paint that comes out of that aerosol, or it's not an aerosol, it's actually like a hydraulic pump. But every speck of paint, every dust, every little bit of paint gets automatically pulled to the car. There's nothing left over. They don't waste any of it on purpose. So all of that paint is perfectly painted on there, and it's permanently attached to it from that electrical charge. All right, so good. The other thing we should note, and you should know this from earlier science, but what do you know about like and opposite charges? Which ones attract?
Positive and negative.
Yeah, opposites attract, and like charges repel. So two positive charges repel, but a positive and negative attract. Okay, and we'll talk more of that with electric forces later on. Okay, and again, the other thing we mentioned is that electricity or charge here is conserved. Charge is conserved. So if one body loses 7 electrons, the other has to gain 7 electrons. James?
So if there's a transfer, it's an attraction between...
Yeah, then there's an attraction. So like, here's an example. You know, give me 2 seconds, and we'll get to that when we get to charging by contact. Remind me, okay? Because I'm going to go through an example there that explains that. Let's talk now quickly, and this is where we're going to pause. We're going to take a look at a video in a minute of the idea of electric charge and how it's what's called quantized. What does it mean to be quantized? What does it mean to be quantized? When you hear the word quanta, what is quanta? James?
I think of an amount of something.
Yeah, an amount. Quanta is an amount. If something is quantized, it means it comes in certain intervals. So like $1, $2, $3, those are quanta. $1.5 would not be quantized then. It's all integer values you're looking for. Now, this is one of the most amazing things that I've started to really read into. And I never knew much about the oil drop experiment that Millikan performed. All I knew is that E stood for what's called an elementary charge. I never knew what it meant. Even in high school, my teacher talked about this, but never went into what it means. And you really need to know what happens here. Here's what happens. The scientist, his last name is Millikan, decided one day that in order to figure out what charge really is, he would perform an experiment. And in that experiment, he charged and we're going to look at a video in a minute to explain this in animation, but he charged particles of oil by a method of ionization, and then put them between 2 parallel metal plates that were differently charged. The lower plate was charged negatively, the upper plate was charged positively. Now, since the oil droplets were all negatively charged, as they fell through an opening, they didn't want to go down to the bottom plate, because remember, likes repel. And eventually, if you change the voltage on those plates to a certain amount, the oil drop will start to levitate in the middle of these 2 parallel plates. It will sit there literally, just sitting there, hovering. Because the gravitational force pulling down was equal to the electric force pushing it away. And there was a balance. It was equilibrium, right? Why am I standing here? Gravity is pushing down, what's pushing back up? Normal force, right? Well, what if there was an electric force and I was a negatively charged ion, and the bottom floor was negative? Wouldn't it push me back up? And it would cause me to kind of hover somewhere? But the upper plate was positive. Okay, so this ion was sitting in space. And due to this, give me a sec, James.
Oh, sorry.
They were able to figure out that the electric charge on each of these oil particles of different sizes in different instances, they took a lot of different data and a lot of different runs through the trials. They were all increments of this number. So for example, if an oil particle had 3 electrons attached to it because of the ionization, it would be triple this number. That would the charge it would determine mathematically. If there were 7 electrons, abundances of electrons on the surface of the oil droplet, there would be 7 times this number. And they kept performing this experiment. Every time they would calculate the overall charge on the oil particle, it was a multiple of this number on the board, which was amazing to realize. Well, why was it a multiple of this number? Because electrons are the fundamental, well, we'll talk about what are really fundamental later, but the fundamental building blocks, electrons, protons, and neutrons of our atom. So because there are an abundance of electrons, if there's 20 electrons, 20 times whatever this number would be the charge. Every time they determined the charge from this experiment, it was always a multiple of this number. So by finding like the least common multiple, they figured out this number. For example, I'm going to put a bunch of numbers on the board, okay?
Sorry, so that's the charge for 1 electron?
For 1 electron, yeah. An electron happens to be, by the way, a negative charge. So an electron would be negative this. What you're seeing there is called really the elementary charge, which is in essence the charge of a proton. An electron is a negative charge, but it's the same thing. They're opposites of each other. Now, look at the following numbers on the board. What's the least common multiple of those numbers? What number goes into all of those numbers on the board? 3. Everybody agree? 3 goes into all of them? 3 goes into 6, 3 goes into 15, 18, and 33. Well, every single time they were able to determine the amount of charge on that oil particle that allowed it to levitate or have an equilibrium stage, it was a multiple of not a number like 3, but this number here. This number that we're talking about was always a factor of the net charge on any oil particle, which enabled the scientists to realize there must be some fundamental building block with a charge of negative 1.6 times 10 to the negative 19 coulombs that is attached to all of these oil particles. And if there's 2 of those charges, then there will be double this number, 3.2 times 10 to the negative 19 coulombs, negative 3.2 electrons. So this experiment is really fascinating to think about. That somebody could say, you know what, let me just try this and come up with all this data and pick up on the correlation that every single data value was a multiple of this number. Especially considering the fact that this was done before really convenient calculators were around, right? You'd have to run this through computers overnight, and you'd wait overnight for it to calculate the least common multiple. Now it's like a joke. Anybody can write a code in like 3 seconds to calculate the least common multiple of a set of millions of strings of data. Whereas then it was a big thing. You'd have to go to, and this is like, I forget if it was in the 60s that he performed this, I think. Anybody have any idea on the history from Millikan? Well, at this point in time, you'd have to like go to a computer, put in your data on a punch card, it would calculate it overnight. It would literally take overnight to actually come up with the answer. So this person, this scientist, had to do this many, many times. So it took him a long time to realize this value. But it was so important to the fundamentals of electric charge because everything at this point is going to be a multiple of this number. Okay? So anytime there's any charged surface, it will indeed be a multiple. And obviously, we could say that there's like 20 coulombs of charge. And 20 is not an exact multiple of this. Okay, it's not an exact multiple, but at that point in time, we're just rounding, right? We're rounding to 20. But in essence, anytime there's a charge on anything, it's a multiple of this number. Because this number is the elementary charge. Why is it called elementary charge? What does elementary mean? Give me more. It's what? Yeah, a beginning or a building block, right? When you go to elementary school, you're learning the fundamentals, right? The elementary things, like elementary particles, are like the smallest, the building blocks. So this is the elementary charge. It's the smallest allowable charge, really, for a charged ion. Okay, 1 electron of abundance. If you have 2, then it doubles. If you have 3, then it triples, etc., etc. Now, are you going to comment about quarks and stuff, and neutrinos and different smaller particles? Oh, okay, go ahead.
I mean, I know about those, I'm not.
Yeah, because there are smaller particles than electrons. You can break them down further, and that gets into a little bit of more quantum physics. Okay, but for the sake of charge, we're going to say this is the most fundamental charge. Go ahead.
I've heard that electromagnetic forces are much stronger than gravitational.
They are, absolutely. Absolutely. We're going to do, you're going to have to just wait, because there is a lesson we're going to do coming up where we calculate the electric force between proton and an electron, and you're going to see the magnitude of strength that's so much greater. We're going to calculate the gravitational force between an electron and a proton. Then we're going to calculate the electrical force. It's so much greater, it's unbelievable. The gravitational force is actually one of the weaker forces that you feel. believe it or not. You wouldn't expect that because that's what you feel, right? But the electric force and the electrostatic force, the weak force, which is a force that's inside of the nucleus, that's also actually stronger than the gravitational force. And we'll talk more about these when we get to subatomic physics later in the year. But we'll get to the electric force and the gravitational force in section 17.2, in the next section, actually. Okay, James? So just, I know, it's really interesting, but hold your idea for a day or two.
I'm just a little confused about the oil thing and floating. So
Let me show a video real quick, okay? Just give me a sec, because I'm going to show a video. So let's pause. Next, let's discuss what an insulator and a conductor is. So an insulator is simply a material that does not transfer charge easily, whereas a conductor is the opposite. It does transfer charge easily. Now, for these examples, what I want you to think about is the fact that most insulators are things like rubber or glass or plastic, whereas most conductors are things like metals. Okay, metallic surfaces usually conduct well, which is why when you look at things like a computer, the motherboard, the things that are actually transferring the electrical charges and the circuits are usually made of some sort of metallic material. Have you ever heard Silicon Valley, that term before? Silicon Valley, what does that make you think of? What does it make you think of when you think of Silicon Valley? Apple computers, right? Computers, what? Hardware, right? Well, it turns out that silicon happens to also be a material that is widely used in semiconductors. Okay, in semiconductors. Let's talk about what a semiconductor is. Who's heard of what a semiconductor is? What's a semiconductor? And don't it's not just a conductor that sometimes does. What more than that?
I think it's like depends on which state it's in.
The state can affect its conductivity, but it doesn't depend on that.
Like it's like sometimes it would something other times it would.
Oh, okay, you don't mean state like gas, liquid, solid state.
No,
You mean
like
what?
depend on how it, I don't know what I'm trying to say, right? Like it's a, like sometimes it can be insulator, sometimes it would be conductor because it.
Depending on what, though. You're right. That's a good lead-in. It can be a conductor or an insulator sometimes, depending on
the charge.
not the charge. Temperature is something in a minute we're going to see. Give me a second on that. That's a good idea. We'll talk about temperature in a second. But what it really is, okay, it's normally an insulator. It's normally an insulator, but if you have some additives to it. So for example, silicon is one of the additives that you'll add to something that's an insulator to make it a semiconductor. Or another one that I wrote down is germanium, another type of atom that can be added to insulators, and then the insulator can act as a conductor.
Isn't that the same column as silicon on the periodic table?
Is germanium the same thing as silicon?
It's directly below it.
Yeah, and usually the families have characteristics that are similar to one another.
Carbon's above silicon.
I'm guessing that it also might even be on the, what's the line that separates metals and non-metals? The metalloids, the ones that are all on that like branch.
Yeah.
It might be on there as well. But certain atoms, when added to insulators, make them conductors. That's what a semiconductor is really. You have to actually change it, okay? It's not like it's just suddenly a conductor. You have to change its chemical makeup. Now, what about a superconductor? Those with computers, have you heard of something called overclocking?
Yeah.
Has anyone ever heard of something and know what overclocking means?
Not exactly. I mean, I think it's you're just running the machine at at a rate that's normally not sustainable.
That's absolutely right, James. You know how it works? That's absolutely right. A computer normally runs at a certain rate. If you can get it to run faster, you're overclocking it, it's called. What do you do normally? What do you notice is on like the side of computer towers when they use that?
Fan. Yeah, fans.
Something to cool it, right?
There's no
What are you doing? You're lowering the temperature. So remember you said temperature, Julie? When you lower the temperature of certain materials, they become almost perfect conductors below certain temperatures. For example, if you run like liquid nitrogen over your processor, it takes a lot of the heat off of it, lowering the temperature of your CPU chip, and therefore you can then overclock the computer. It runs much faster than normal computers would because there's almost zero resistance in the flow of electrons. So a superconductor is a material that when lowered to a specific temperature has almost no resistance whatsoever to electric flow. We're going to learn about circuitry, and we're going to learn about something called resistors. Everything is really a resistor. Even your body resists some flow. Insulators are really high resistors. They resist all flow. Now, if you could resist no flow, which is theoretically impossible, but realistically it could almost be done by creating what are called superconductors, by lowering the temperature so much that the flow of electrons is no longer impeded.
I think there was this like game like in 2007 that came out. I think it was like only a PC game,
Uh-huh.
but there was only like one type of computer that could run it because like
Because the processing that was involved probably with the video processing and the
Yeah.
sound. Yeah. Now I'm sure it can happen, you know, it can be used on a lot of computers, but yeah, you're absolutely right. Anybody have a gaming PC? If you have a computer that could run games and stuff, traditionally you have a high processor. You can run at faster speeds. Absolutely. That's an example of that.
like Alienware or something like that. Like,
Yeah, one of those computers that usually people that have gaming computers make them themselves because they build them and it's a lot cheaper to build yourself. If you buy a computer that could support certain games now that are like online games, those computers would be ridiculous amounts of money. So people would make them themselves, and Alienware was a brand that a lot of people did.
Yeah, and the Alienware computers have the liquid nitrogen running through their towers to keep it cool.
And that uses electricity to constantly absorb heat. It heats up the liquid nitrogen. And then there's a coolant chamber, and that's a thermodynamic cycle that's occurring there. We'll talk about that. Well, that's in one of the videos I recorded additionally. All right, let's go on to the next thing. We talked about the fact that in the beginning, one of our objectives was to distinguish between charging by contact, charging by induction, and charging by polarization. So let's talk about charging by contact first. And James, this was the example before that I said hold off for a minute, okay? So imagine if you rub a balloon on your hair. What happens? Hair starts sticking up. It gets pulled toward the balloon, right? I don't have a balloon. I wish I did. I gotta get a balloon I can show you, but obviously you've seen this before. So what happens is the electrons jump from one material to the other material. So one of those materials is suddenly an abundance of electrons. So its charge is negative. It has an abundance, right? And a bunch of extra electrons. So it's a negative charge. What about something that is missing electrons? Positive. So if your hair's electrons jump to the balloon, your hair is a positive charge, and the balloon's negative. So what's going to happen then? Yeah, if they're opposites, they attract. That's why when you keep the balloon near your hair, after rubbing it on your hair, you're going to see your hair get pulled toward it, right? Now, what you've done is you've charged that balloon by contact. That's what charging by contact really is. And traditionally, you charge insulators by contact. Because the conductor won't get charged, that flow will pass through it.
Wait, so what stops the electrons in the balloon from just discharging to your hair? Like instead of like just attracting to it, but instead of just
Your hair and the balloon are both insulators. So it's not going to naturally want to jump from one to the other. When you rub it, when you agitate it, you're rubbing those electrons off onto the balloon. The physical force is causing it. Now, if you just touch them together, it's not going to jump from one to the other because they're both insulators. They're both still charged. One has negative charges, one has positive. They pull together, but they don't hop from one another there. It's the actual agitation that's causing that
Yeah, but I was
charge.
just wondering why it wouldn't just go from one to the other and equalize it.
Because of its conductivity. If one was a conductor, it would just jump from one to the other initially, automatically. So if I were to, again, remember when I told the example before with Gio, when I went like this on the ground, I was charging my body up with negative charges or positive charges, depending.
But your shoes are rubber, so
The shoes are rubber, but the actual remember what I'm talking about right now, charging by contact with two insulators. What did I just say? A balloon in your hair, they're both insulators, right?
Oh, so they can't.
The ground and my feet are both insulators, but I can still charge them up. And then that charge can transfer from my shoe into my body here, and then I could touch Geo. It didn't work that time, but because my body is a conductor. That's your question, James. That's the charge isn't gonna jump back into the floor. It's gonna transfer into my body, which is a conductor itself. Okay. The second part I wanted to talk about was the idea that the earth is a grounding for you. So if you were, you trying to do it? It's not right. You really got to do it on like a carpet floor.
Don't
It
you
works
get
a lot
scared,
better.
like before you touch, so you get like
You might,
you
yeah.
get excited.
Whenever I open the door in the math science office, every time I open the door because it's a rub and the carpet on the ground is like really static, has a lot of static electricity when you rub. When I get up and stuff, if I walk over, I get zapped every single time, and it's so annoying. And I know it. I'm like walking over the door and I'm thinking, I'm like, it's gonna happen every time. They're like zaps, and it's so annoying. So I got to the point this year where I just go like this, and I feel it every time. But you just get used to it. And it doesn't hurt. It's just annoying more than anything. But it builds up every single time.
Next time.
Let's see. All right, let's go on to the next thing. We'll come back. Let's go on to the next thing. Let's talk about induction. Induction is really interesting. And the idea of induction here, has to do with grounding. That's why I talked about the earth being a grounding source. So let's take a look. First, we can read this, but let me talk. The idea is this. If you can charge a particle or an object that's an insulator. So take a look here. We're looking at, in this case, and this a lot of the time, glass is a good insulator to carry static charge, so you use glass. So this is just a glass rod. Now, you charge the glass rod with a negative charge, maybe by using a piece of fabric or wool on the surface of the glass. You can rub it on the surface of the glass, and it causes it to get charged. Now, when you bring that charged glass rod near a conductor, like a metal sphere which has electrons in it, the electrons don't want to be near other electrons, right? So what do? They all move over here. So all the electrons inside of here automatically move this way. So there's a net positive charge over here and a net negative charge over here. And it makes the metal become polar, right? When things are polar, it means there's a positive on one end and a negative on the other end, like batteries. They're polar. They have poles. So this is what happens. Now, while this is happening, again, you're not touching. This is not touching. Notice, these are never touching one another. Never touching. So what you do is you keep the glass rod nearby, so it causes this pole, this separation to exist. Then you attach a wire, and that wire allows the electrons to flow out of the conductor into the ground. So these electrons flow into the ground. This is the symbol for grounding on schematics. So they flow into the ground. When they flow into the ground, what's left is an overall positive charge, right? And then when this insulator that has a negative charge is removed, all that's left is these 4 positive charges, and they spread out now. So what you've done is you've charged this conductor temporarily by what's called induction. And you've charged this conductor here temporarily by induction. So in the last example, charging by contact, we charged an insulator, and now we're looking at how to charge a conductor. James.
So if you're charging this by taking out electrons and you're leaving behind the protons, the charge of anything depends on the number of protons from the element.
Yeah, but the element, so say this material has a certain amount of protons. I don't know, pick a number, 10. It doesn't make a difference, right? And you lose 3 electrons to grounding. Now you have a net 3 positive charge. It's the lack of electrons that are caused.
That's the maximum positive charge that you have, 10 charges.
Sure, because 10 is the maximum amount of electrons you can lose.
Yeah.
You can think of it both ways. Yeah. You see what I'm saying? But try to think of it as negative loss as opposed to positive gain. You follow the difference? Yeah. Okay, losing negative is really a positive gain, right? What's minus a negative become? And you're losing negative charges, aren't you? So you're gaining a positive charge, but think of it as losing negative. Think of it conceptually that way, okay? But yeah, you're absolutely right, James. Let's get to the last topic. I don't know if I'm going to show you that second video again, and then I'll hand back your stuff while I'm showing the video. I'm going to show a video about induction in a minute. I'll go back and we'll show that video. Let's look at polarization, though. Polarization is the easiest of all. Polarization, the interesting part, first of all, again, it's insulators. So we're back to insulators for polarization. But for polarization, you're not actually changing the net charge on something. For example, take a comb, brush it through your hair, okay? The comb gains a positive charge. That's the charged object over here. Then bring the comb near a bunch of confetti or piece of paper on the table. What happens with this piece of paper? What do they normally do?
Oh, they stick to it.
Yeah, they stick to it. They jump. They jump, and the reason being is this. The charged object is positive. And in insulators, the material in some insulators that they're made of have dipoles. And those dipoles automatically align themselves so that the negative part of the pole is on the surface and the positive part is away from the surface. Because remember, positive wants to attract negative. So it causes these dipoles to be induced. And these induced charges, again, it's not induction. The word induction really means no touching. That's the idea of induction. Like inductive reasoning has to do with reasoning that's not direct as opposed to deductive reasoning. So they're considered induced charges, although we're calling this polarization, not induction. So you bring this charged object near it, it causes the dipoles to align, and if those poles are aligned on enough of them, they kind of jump toward it. But again, there's no touching necessary. It might touch in the end, it might jump toward it, but it's not necessarily needed to do it. The other thing is that there's no net charge induced. There's still an even charge. This insulator right here that I'm pointing to is still neutral. It's just that on the surface, all of the poles that are negative lined up, and in the inside, all the positive poles lined up. That's all that's happening. but there's no net charge here. Whereas a moment ago for induction, when we grounded the metal sphere, all the electrons flowed out. So it created an overall net positive charge on that sphere. Here, it's not creating a net charge. It's just causing a realignment of the molecules. They're dipoles.
How come when you brush your phone through hair it becomes positive or?
That's charging like contact. When you're brushing it, the electrons are moving from one surface to the other. They're both your hair
Becomes
and your comb are both insulators. When you rub them on one another, the electrons jump from one surface to the other.
So your hair would become negative.
If the comb became positive, your hair become negative. Yeah.
Okay.
Yep.
Would there be a way to like have like let's say positive blue paint and positive like red paint, and then you mix them and somehow you separate, like it becomes perfect?
They wouldn't be mixed. They couldn't. If they were both positively charged, they would repel
No,
each other.
one's negative, one's positive.
Oh, then you can mix them together, sure.
And then would you be able to split them back up, or no?
Depends. I don't really know too much about that. I don't think you can split two paints up once you mix them together anyway, right? Once you make when you're like
I was asking like,
because the charges you're saying, could you split them up?
yeah.
I don't know. Theoretically, I guess, but realistically, I thought once you combine paints, they become like one. I'm not sure. Remind me, please, to show you guys. Actually, you know what? We have a double this week in this class. The other class doesn't. So on the second period of the review day this week, we're going to review the first period tomorrow. In the second period, I have like a playlist of a bunch of videos from YouTube.
Day one.
You don't have a double tomorrow? Why did I think you had a double?
Our double is day 3.
You just got really disappointed.
Oh,
The other
man.
classes
I miss you,
still.
sir.
Maybe. No, day one.
Nope, day three.
Day 1, we have
Yeah.
first period.
Day 3.
Day 3.
I thought we had a double tomorrow. You're right. I don't know why I thought that. Okay. Well, I'll show you this video. I'll show you this video another time for sure.